Whilst browsing past papers for a suitable example to use in this video, I came across this beautiful little question. In the practice papers for the Cambridge International A-levels, the syllabus is exactly the same as for the UK A-levels, but the international papers are generally a little bit more difficult. Now, it is based on proof, mathematical proof. A subject which used to be standard fare in A-levels when I was at school, but which disappeared when A-levels became modular. Well, it's now back, and I must say I'm delighted to see it back. Now, here we have the relevant section of the specification, and it is common to all of the examination boards. It specifies proof by deduction, proof by exhaustion, disproof by counterexample, and proof by contradiction. There is one other method of proof by induction, but that is part of the further maths syllabus. This particular question deals with proof by contradiction. There we are, proof by contradiction. And it specifies including proof of the irrationality of root 2. And I'm going to start this video by doing that proof, because all proofs by contradiction are based on exactly the same idea. I will then go on to do the question. The proof that root 2 is an irrational number is a model for any particular proof by contradiction, but in particular the question upon which this video is actually based. And what we do is we have to prove that root 2 is an irrational number, so we suppose the exact opposite, that root 2 is rational. And by a series of genuine, correct mathematical steps, we create a contradiction, which means our supposition must be wrong. So if we suppose that root 2 is rational, then root 2 must be of the form p over q, where p and q are integers with no common factor. Well, what we do now is we just play around with this expression algebraically, and the first most logical step is to square both sides to get rid of the square root. So 2 is p squared over q squared. The next most logical step is to multiply by q squared, both sides, and we get 2q squared equals p squared. Now that tells us something. That tells us that p squared is even. Now p squared could only be even if p itself were even. If p were odd, an odd times an odd is an odd, so p therefore must be even. That means that, I'll go back up here, that p is 2r, where r is an integer. It's twice something. Now we had in this line 2q squared equals p squared, so 2q squared is 2r all squared, which is 4r squared. So q squared must be 2r squared. So q squared is even. So q is even. Now what we have now is that p is even and q is even. So p and q have a common factor. Well, that can't happen. So there's a contradiction. That's the symbol I use for contradiction. And the conclusion is that by contradiction, root 2 must be irrational. Beautiful proof. And a similar proof will prove that root 3 is irrational, root 5 is irrational, the root of any prime number is irrational. Let's now prove that 3 plus 5 root 2 is irrational. We do it in exactly the same way. We suppose that 3 plus 5 root 2 is actually rational. We assume the complete opposite. In other words, 3 plus 5 root 2 is equal to p over q, where p and q are integers. That means that 5 root 2 would be p over q minus 3, which can be tidied up to p minus 3q over q. And root 2 would be p minus 3q over 5q. But p and q are integers, so p minus 3q is an integer, 5q is an integer, and therefore root 2 is a rational number, which it isn't. So we have a contradiction. And the conclusion, therefore, is that 3 plus 5 root 2 is an irrational number. Now, we could have done exactly the same proof for any number of the form a plus b root 2, where a and b are themselves rational. So there are infinite number of irrational numbers of that form, and similarly there'd be an infinite number of irrational numbers with root 2 replaced by root 3, or root 5, or root 7, or root 11, or root of any prime number. And just before I do the example which we originally set out to do from the examination paper, let's just look again at the extract from the specification. And it specifically stated proof by contradiction, including proof of the irrationality of root 2, which we've done, and proof of the infinity of primes. And I attach below that the proof that the number of primes is infinite. We begin by supposing the exact opposite, that is, that the number of primes is finite. And I've called them P1, P2, P3 up to Pn, where P1 is the smallest, 2, P2 is 3, and so on, and Pn is the largest prime. But consider the number where all of those primes are multiplied together and 1 is added. This is not divisible by any of the primes that we already know, P1, P2, P3, up to Pn, so it therefore must be a prime number itself. But that contradicts the fact that Pn was the largest known prime. So it's a contradiction, so the initial assumption must have been wrong. In other words, the number of primes is infinite. And now at last we come to the question which is the subject of this particular video, and we're required to prove by contradiction that log to the base 10 of 5 is an irrational number. And like all of the examples I've covered, we begin by supposing the complete opposite, and that is that log to the base 10 of 5 is rational. That means that log to the base 10 of 5 is of the form p over q, where p and q are integers. Now, if you'd like to try this question for yourself, I suggest that you pause this video at this particular moment and then carry on once you've done it after I've revealed the answer. I'll wait a couple of seconds. Now, the only thing that we can actually do with this particular expression is to invert it, that is to write it the other way round. And 5 is 10 to the power p over q. Those two statements, log to the base 10 of 5 is p over q, and 5 is 10 to the power p over q, are inverse statements. Now, we have here a rather frightening looking index, a fractional index. So let's get rid of it. Let's get rid of it by taking the qth power of both sides of the equation. And we get 10 to the power p over q to the power q, which is 10 to the power p. So 5 to the power q is 10 to the power p, but 5 to the power q is an odd number. and 10 to the power p is an even number, which is an impossible situation. We cannot have an odd number equal to an even number, so we have a contradiction. And so we have, by contradiction, log to the base 10 of 5 must be an irrational number. Very, very beautiful and very simple proof. Remember, it comes from the Cambridge International A-Level practice papers. Generally, they are much harder than the UK A-Level papers, and this particular practice paper was designed specifically to be the hardest of the lot. I hope that I've shown that in fact it's nothing to be frightened of and is really quite easy once you have practiced one or two questions of this type. Now, I hope that you found this video useful. If you have, head across to my website, where there are many more A-level questions covered in detail, each with associated graded exercises and additional and sometimes humorous background material. There's also a growing list of videos similar to this one. To view them, go to youtube.com and search Fred the Mathematical Fly. Many more videos are planned, but if there's one particular question that you need help with, then email the details to me, and I could consider making it the subject of a future video. Alternatively, and for a quick response, I can arrange a personal live video lesson done in exactly the same style.